Welcome to EPG Pathshala. In this module, we are going to look at the GLM function for count data in R. As you know, the LM function is a very fundamental function of R which is used to fit linear models, and there are many useful things which you can learn by focusing on the LM function. It will give you a good idea of how to extract information from an R object and how to get several things of interest such as the coefficients, the residuals, the predicted values, standard errors, tests of hypothesis, and so on. The extension of the LM function when we fit a generalized linear model is the GLM function. You will see that it is very similar to the LM function, and learning to manipulate this object will also help you to manipulate many similar regression objects, say for example the GLM function, which you may use later in R. In this module, we shall look at the GLM function for count data using an artificial data set which was obtained from the UCLA website. I have indicated the exact website in the slides. It looks at the number of awards which a student has won in high school as a function of the particular academic program the student is in and a function of his math score. We shall try to build a regression model, look at the coefficients, see their interpretation. We shall recover the deviance object from the output and look at several alternative ways of presenting the output. So for example, we could just run a summary of the GLM object and look at the coefficients, or as is more informative, say for example for epidemiologists, we could present the information in the form of incidence ratios, or we could also plot the data to give a more intuitive feel for the results. Finally, we should look at some alternative extensions when we have count data, and we shall revisit most of these extensions in subsequent modules in this paper. Learning objectives for this module. First, we shall perform some exploratory data analysis using R on a simulated data set which was obtained from the UCLA website. Next, we shall fit a Poisson regression using GLM. We shall look at alternative ways of presenting the output. And finally, we shall look at some alternative formulations for the case where we have a count variable as an outcome. The GLM function in R for count data. The dataset in question here looks at the number of awards earned by high school students as an outcome variable. You can see immediately from here that this is in the nature of a count variable, and rather than normal regression, we need to go for a count regression model such as a Poisson regression. We have two predictors. The first is the type of program into which the student was enrolled. This could be vocational, general, or academic. And the second predictor is a continuous predictor which represents the score obtained by the student in their final examination in mathematics. The dataset and the case study was obtained from this website from UCLA related to a vignette which illustrates Poisson regression. Description of the data. So first, as I said, this is a simulated or artificial data set. The outcome variable is called num awards. So num awards is an outcome variable which is the number of awards earned by a student at high school in a year. The two predictors are classified as MAP, which is the student's score on their math final examination, and PROG, which is a categorical predictor variable with 3 levels. 1, if the student was enrolled in a general program. 2, if he was enrolled in an academic program. And 3, if he was enrolled in the vocational program. We shall start by looking at the summary statistics for the data set. So here first we have used the read.csv command to directly read in the data from the website, and we have stored this in the R object P. Next we have used the syntax P. Within P, prog is a factor with program levels equal to 1, 2, 3 and the labels equal to C, general, academic, vocational, and ID is a factor ID. This tells R that two of the variables are not to be regarded as continuous but as factor variables. So program has 3 levels and R should consider the corresponding labels as general, academic, and vocational. When we do a summary of P, this is what it returns. So the first column is the summary of the ID, which is irrelevant, but the next 3 columns give the summary of NUM awards, program, and map. So for NUM awards, for example, you can see that the median number of awards is still 0. The mean number of awards is 0.63. So this suggests that the data is slightly skewed because the mean is larger than the median. The maximum awards is 6 while the minimum is 0. For program, we get the frequency distribution. So there are 45 students in the general category, 105 in the academic program, and 50 in the vocational stream. For math, we can see that the minimum score is 33, the maximum is 75, the mean is 52.6, and the median is 52, which are reasonably similar. We can also use the GLM function to find the covariances and variances, and a notable feature for this data is that the unconditional mean and variance of the outcome variable, which is the number of awards, is similar. And the reason why this is important is that we know that if we have a Poisson distribution, the mean and the variance should be the same. However, what we're really interested in looking at when we fit a regression model is the conditional summaries. So from the outcome on the previous slide, we can see firstly that program type is a good candidate predictor for the number of awards. The mean and variances within each level of program are similar. And we have also plotted the conditional histogram separated by program type. This was obtained using the TApply function. So the syntax is given on this slide. With P, the function which we use to apply using TApply is sprintf msd equal to %1.2f mean x and standard deviation x. This returns the mean number of awards for the general, academic, and vocational categories, which you can see are 0.2, 1, and 0.24, and it also returns the standard errors in parentheses. So 0.4 for general, 1.28 for academic, and 0.52 for vocational. As I said before, you can see firstly that the number of awards appears to be quite different depending upon the nature of the program, and hence our conclusion that program type is a good candidate predictor for the number of awards. Secondly, the means and variances within each level of program are similar, so 0.2 and 0.4 for general, 1 and 1.28 for academic, and 0.24 and 0.52 for vocational, so there is close agreement for each of the 3 categories. And finally, we shall also plot the conditional histogram of the number of awards separately for each program type. This can be done using a very good plotting package, which is the ggplot package. We shall spend some time on the syntax for this package in the paper on advanced R. Now, of course, we could have also done it using the regular plot, but the ggplot returns an attractive plot. The syntax is given on the right panel on the slide. So here we have the number of awards on the y-axis, the frequencies, and we have 3 separate bars corresponding to a pink bar if the student was in the general category, a green bar for the academic category, and a blue bar for the vocational category. So from here you can see that the green bars are relatively spread out, and relatively shifted to the right, suggesting that those in the academic program tend to win a larger number of awards. Those in the general program are generally restricted in the first two categories, 0 and 1, and vocational is slightly better at 0, 1, and 2. So let us next fit a regression to this data and see if our conclusions from the exploratory data analysis hold out for the regression model. So firstly, there are many alternative regression models which can be fitted to the data. The simplest approach is to use an OLS regression. We do not use the OLS regression on the counts because we know that counts will tend to be heteroscedastic. One relatively easy but ad hoc way to get rid of the heteroscedasticity is to log transform the counts. This will also help to reduce the skewness in the data. However, there are still issues. Firstly, there is loss of data due to the fact that we have 0 counts, and applying 0 reduces the outcome to -infinity, which needs to be disregarded in the regression. We can of course add an ad hoc constant like 0.5, but this will tend to be highly influential on the results if we have a large number of zeros. Actually, for the situation where we have a large or an excess number of zeros, qualifies for an additional regression model called ZIP model, and we shall revisit this later. So although OLS regression can be a useful starting point, there tend to be many issues with these kind of models. Firstly, as I said, the loss of data. Secondly, the heteroscedasticity of the count. So if we have a mean lambda I, then we would expect the variance of the count also to be lambda I, where lambda I is a function of the covariates xi for the ith individual, and thus we have different variances for each individual. We can reduce this somewhat by the log transformation, but often the adjustment is incomplete and we still have some residual heteroscedasticity. So note, in this case, it is not really possible to use the usual transformations used to tackle heteroscedasticity because we do not have the typical form of the heteroscedasticity as a constant times some known function of the covariates. There is also the issue of skewness, which is reduced to some extent by considering log transformed counts, but not completely. The second and the common tool is Poisson regression, and this is what we shall concentrate on in this module. Another alternative could be negative binomial regression. Negative binomial regression is also applied to count data. However, it is generally applied in the situation where we know that we have over-dispersed count data. By over-dispersion, I mean that the variances tend to be larger than the counts. There are several alternative ways to tackle this. One is quasi-regression, which we shall visit in a subsequent module, but a simpler alternative could be negative binomial regression. The way the negative binomial model handles over-dispersed count data is that it allows for an extra parameter to model the over-dispersion, and in the case where we have over-dispersed count data, the confidence intervals obtained using negative binomial regression will tend to be narrower than those obtained using Poisson regression. Finally, we have zero-inflated regression models, which are the ZIP models, which I mentioned earlier. ZIP models are used when we have excess zeros in the data. We make a distinction between true zeros and excess zeros. That is, we assume that the population is not really homogeneous, but is made up of a mixture of two populations, one of which is discrete at 0. So in this case, it would represent a group of students who never receive awards and a group of students who receive awards. For the second category, we would assume that the distribution is Poisson, while for the first, it is degenerate at 0, and the overall population is made up of a mixture of these two groups. In a subsequent module, we shall look at ZIP models, the model, the fitting, and alternatives such as the hurdle regression models. Let us consider the typical syntax for the GLM function for count data. So here we have used the GLM function and fitted the regression num awards tilde prog plus math. Note that we have told R before that prog is a factor. We have said family equal to Poisson and data equal to P. We have not specified any link function, and the reason for this is that we wish to use the default choice of link, which is the log link. So if no link is specified, R will by default use the log link. We have stored this GLM object in M1, and the syntax given on the first line of this slide at once defines M1 and also implements the summary command on the M1 object. So running this command will lead to the output given on the subsequent portion of the slide. So first we return the function call. Next we see the deviance residuals or a summary of the deviance residual. We get something called coefficients. There is an intercept. There are two coefficients for program academic and program vocational. So note that general has been used as a reference category, and academic and vocational correspond to the coefficients of two dummy variables for each of these two categories. And also we have a coefficient for the math variable, which, as you recall, is continuous. For each of these there are 4 columns giving the estimate, the standard error, the z value, and the corresponding p values. So you can see that intercept, academic, and math are all statistically significant, and this is marked by a certain number of asterisks. The explanation for the number of asterisks is given below. So for example, 3 asterisks mean significance is the 0.001 level, and so on. Below this output there is an important line which says that the dispersion parameter for the Poisson family was taken to be 1. The dispersion parameter is a constant which is assumed to transform the mean into the variance. That is, we assume that the variance is some theta into the mean, where theta is considered to be the dispersion parameter. You know that here for the Poisson family, the dispersion parameter is given by 1. Next we get a set of deviances. So we get the null deviance, which here is 287.67, and there is a corresponding degrees of freedom 1.199. We also get the residual deviance, which is 189.45, and the corresponding degrees of freedom is 196. We get the value of the Akaike information criterion, which here is 373.5. And finally, the output reports the number of Fisher scoring iterations which it took to fit this model, which is in this case 6. Cameron and Trivedi in 2009 recommend the use of robust standard errors, that is, standard errors which are robust to slight misspecifications of the assumption that the means and the variances are identical within each category of the covariate. The robust standard errors can be obtained using the R package sandwich. So here we have defined an R object cov.m1 and used the vcov8c function on m1 and type equal to 8co. We find the standard error from the cov.m1 object and create a table using the cbind command r.est. So r.est reports as before the estimate, which is unchanged, the robust standard error, the probability, which is of course changed because the standard error is changed, and the lower confidence interval as well as the upper confidence interval. It is a good exercise for you to compare the standard errors using the robust method to those obtained using the inverse information method given on the previous slide. So once more, a summary of the GLM output. At first, it echoes the function call. It gives information on the deviance residuals. Now note that the deviance residuals are approximately normally distributed if the model is specified correctly. So here it appears to be reasonably normal, but shows a little bit of skewness since the median is not exactly equal to 0. The next set of output is the Poisson regression coefficients along with standard errors, z-scores, p-values and 95% confidence intervals. We can see here that the coefficient for the variable math is 0.07. We can also see that the indicator variable prog academic compares between program equal to academic and program equal to general, and the expected log count for program equal to academic increases by about 1.1. The indicator variable prog.vocational is the expected difference in log count between program equal to vocational and the reference group program equal to general, and so on. The deviance, we have seen that the GLM returns two values of the deviance. We can use the residual deviance to perform a goodness of fit for the overall model. Now, the residual deviance is the difference between the deviance of the current model and the maximum deviance of an ideal or saturated model, where by saturated we mean that the predicted values from this model are identical to the observed values. So the goodness of fit chi-square test is not statistically significant, and this means that the model is a reasonably good fit. In the case when the model is not a reasonably good fit, our next options would be to look at whether there are omitted predictor variables by using the update function on the GLM object. If our linearity assumptions hold, this can be done in a number of ways. If we know the type of nonlinearity, we could use the nonlinear functions in the formula. Else, we can use options like GAM. And finally, if there is an issue of over-dispersion, which we shall look at in great detail in some following modules. So here we use the width M1 cbind, define the residual dot deviance, the df, the p chi-square for the p-value, and we see that the p-value here is 0.6182, suggesting that the residual deviance is not statistically significant. We could look at the overall program effect. Now note that we have two coefficients for each of the programs. So rather than see which program is different, we might want to know one single answer for whether or not program has a statistically significant effect on the number of awards. This can be done by comparing two deviances. That is, we compare the deviance of the full model with the deviance of the model which excludes program. This will lead to a 2-degree of freedom chi-square test. So this has been done here using the update command to refit the model, eliminating program. And then we use the ANOVA object on the M2 and M1 object and test equal to chi-square. The result we get is something very similar to the ANOVA object used in case of linear models, except that here it is an analysis of deviance table rather than an analysis of variance table, and we see that the difference is statistically significant with a probability p-value of 0.00069. So the significance of this chi-square test indicates that program is, in fact, a statistically significant predictor of NUM awards. One way to present the output could be to present it in the form of incidence rate ratios. These are obtained by exponentiating the coefficients. We would, of course, have to obtain the corresponding standard errors and confidence intervals. This can all be done clearly by calling the R package MSM. This is a function delta method, and here we have used the delta method on the M1 object and stored the results in the R object S. The syntax here returns the incidence ratios and their standard errors, lower confidence intervals and upper confidence intervals. So for example, the output indicates that the incidence rate for the program equal to academic is 2.96 times the incidence rate for the reference group program equal to general. We could also look at the marginal mean. So for example, what are the expected counts for each program type, holding math score at its overall mean. This can be used by using the predict function. So first we have constructed a data frame where math is held constant at its mean, $math, mean of $math, and program is a factor with 3 levels. So here you can see the S1 data frame. We predict using the model M1 on the data frame S1. We wish to predict the response, so we say type equal to response and se.fit equal to true, so as to return not only the predicted values but also the corresponding standard errors of prediction. The results are as given on this slide. So you can see here the predicted number of events for level 1 of the program is about 0.21, holding math at its mean. For level 2 it's 0.62 and for level 3 it's 0.31. If we take the ratios of these predicted counts, it matches what we obtained before using the incidence rate ratios. We could also do a plot of the predicted events. As before, we do it using the ggplot command and the syntax given on the lower part of this slide, and the graph indicates that the most awards are predicted for those in the academic program, especially if the student has a high math score. The lowest number of predicted awards is for those students in the general program, which is program equal to 1. So here is the graph obtained using ggplot. On the x-axis we have plotted the math score, and the y-axis we have plotted the expected number of awards. In each case we have a curve which is monotonically increasing. The green curve, which corresponds to academic program, lies above the blue curve, which corresponds to the vocational program, and this in turn lies above the red curve, which corresponds to the general program. Finally, a few things to consider when we are fitting a regression model to count data. Firstly, when it appears that the conditional mean and the conditional variance are not quite similar, that is, there is some issue related to dispersion, we should first go back and check if the model is appropriately specified. What this means is that we should look first whether any important variable has been omitted or whether the functional forms are correctly misspecified. Assuming that the model is correctly specified, we should next group the data and run a check of the assumption that the conditional variance is equal to the conditional mean. Since that there is over-dispersion in the data, there are several packages, R packages, which would provide tests for over-dispersion. So for example, the R package PSCL provides a test using the function OD test. However, another common cause of over-dispersion could be excess zeros, and there are specific ways of handling this, such as zip models and hurdle models. Now, count data often have an exposure variable which indicates the maximum number of times the event could have occurred. So for example, if the count is mortality, then it is capped by another count, which is the corresponding population size, and in this case, this exposure variable, in this case the population size, should also be entered in the model as an offset. We have explained this in some detail in our preliminary modules on count regression. So here we would prefer to model the rate rather than the mean count. Finally, as related to goodness of fit, we have used the deviance, but there are also some different measures of a pseudo R squared. So note that it is pseudo because we no longer have the linear model decomposition into several vector spaces and so on. We have not used least squares but maximum likelihood for the fit. And finally, note that Poisson regression is estimated by a maximum likelihood estimation, and hence it requires a large sample size. In the case where we do not have a reasonably large sample size, we could opt for estimation and inference methods for exact sample size data. In this model, we have looked at the GLM function in R for count data. This has been done using a simulated data set on the number of awards won by a high school student in relation to the program in which the student is enrolled, that is general or academic or vocational, and the score obtained by the student in math in the final exam. So to begin with, we have looked at an exploration of the data using the summary command, the tapply function to get conditional summaries, conditional histograms. We have checked if the typical assumption that the mean equal to variance holds for this data and have been satisfied. Next, we have considered alternatives. The simplest alternative would have been to log transform the data and fit an OLS regression. It would have reduced the problem to one which we already know using the LM command. However, there are often many residual issues with this model, in particular that the assumption of heteroscedasticity, the assumption of normality are often not met and are often incorrectly or inadequately adjusted for by taking a log. We can also lose substantial data in the case where we have excess zeros in the model. And in fact, we have seen that in the case where we have excess zeros, we should actually be going for other alternatives such as zip models or hurdle models. Next, we have used the GLM command to fit a regression to the data set, and we have looked at each of the lines of output. We have seen that an alternative method could be to present the incidence rate ratios, and we would also need to transform the confidence intervals, the standard errors, to this scale. This can conveniently be done using the delta method function. We have seen how to get robust standard errors, and finally, we have seen how to use the predict function in R to get the predictions and standard errors, and how to plot these predicted values to get an intuitive feel for the results. We have also presented a list of things to consider for the case when we have a count outcome, and we shall return to many of these in subsequent modules.